Yesterday we have studying quantum field theory, and we have given some rules to build the Feynman diagrams and the amplitudes, and now we want to make these things more precise. So S is the scattering matrix. And let us write it as 1 plus IT. IT is what you compute by means of Feynman diagrams. Then we will see how to compute Feynman diagrams, but these are the diagrams. One we have already computed. For example, this is a contribution to IT. One is the S matrix of a free field theory where no interaction occurs, and so that's the trivial part. So you isolate the trivial part of the scattering matrix by writing it as 1 plus IT. And then unitarity, S dagger S equal 1 can be written as 1 minus IT dagger times 1 plus IT. And when you multiply, you have 1 plus IT minus IT dagger plus T dagger T. And so from this identity, you see you have 1 on both sides, and you can simplify it, and what you get is this identity, IT minus IT dagger equals, let's move T dagger T to the right hand side, minus T dagger T. And this identity is known as Optical Theorem. And it has a diagrammatic version, can be written as a property satisfied by each Feynman diagram. But let's apply it to this simple Feynman diagram. So this diagram is our IT for the moment. So let's take IT equal to that diagram, which is minus I lambda squared divided by P squared minus M squared plus I epsilon. Then the identity, the optical theorem, tells us that IT minus IT dagger, that is the real part of IT, twice. So twice the real part of that is negative definite. Whatever it is on the right hand side, that's minus T dagger T. So we must have twice the real part of IT negative definite. And we can use the identity we wrote the other time that says that this thing is the principal part of 1 over x, principal value, plus I pi delta of x. And we apply it to our diagram. Our diagram is minus I lambda squared times something like that. So you have minus I lambda squared, principal value of 1 divided by P squared minus M squared, And then you have minus I lambda squared, but times I pi. Actually, there is a minus because you have to conjugate this distribution here. So if you conjugate it, here you will have plus, and there you will have minus. So with the plus you have minus I pi, minus I lambda squared times minus I pi, and that is minus lambda squared pi. Let me write it. Delta minus m squared. So we are using this identity. Now, the optical theorem tells us that twice the real part must be negative definite, and indeed twice the real part is given by that, which is negative definite. So this twice the real part is the contribution on shell. And second, it tells you that you cannot, well, first you have to have a plus I epsilon or something, because otherwise you don't have the contribution on shell, which is the particle. Second, you cannot change the sign here, because if you change the sign of that, minus I epsilon, you would have a plus, and you would violate the optical theorem. Third, you cannot change the sign, the overall sign of a propagator. You cannot change the sign in front because you would violate the optical theorem. You could change both signs, however. You could change a sign here and a sign there. So the propagator must be what we wrote. So there has to be a plus I epsilon in the scattering interpretation, and it has to be plus I epsilon. This is okay. This is not okay. This is not okay. But this is also okay. Okay with unitarity. Well, it turns out that they cannot coexist. They cannot live together in the same theory, but they are both useful because they are, one, the propagator that appears in the S, and the other one is the propagator that appears in S dagger. So they coexist in the identity involved by the optical theorem, but in the Feynman diagrams they cannot because of some mathematical problems that arise when they are both there, at least if you do not treat them properly. We will see at the end that actually the solution of the problem of quantum gravity, it will be the unique way to make them coexist. But naively they cannot. So unitarity tells you, gives you constraints on even the free propagator, and when you build Feynman diagrams, you can work out physical processes relating some incoming particles and outgoing particles that you compute by means of Feynman diagrams. So that is your IT. And the optical theorem will tell you that this object. Actually, this is an identity that holds diagram by diagram, if we want, but anyway, plus its conjugate. So this is IT plus its conjugate, which is minus IT dagger. And that will be a process where you exchange out with in. There is a transpose, and you take the dagger, so there is also a conjugate. That is equal to minus T dagger T and that is equal to some identity where your in states, so you have a cutting of your diagrams, and let's say that you compute this object. This is a matrix, so you compute some something like this. You take two states, alpha and beta, and you insert IT between a bra and a cat. Then you can write that as a sum over all intermediate states with by means of a completeness relation. You insert 1. And each of those you can see as a diagram itself. So it's this part of the diagram and this part of the diagram. So there is a cut in between, which is what you insert there. And you can formulate this, the optical theorem, in a diagrammatic way. Well, to make the story short, what you get here in the cuts tells you what the physical states are. And the reason is that what are the in states and what are the out states? The in states and the out states are the states of your theory, and the point is that in physics many times we need to work with redundant sets of things and then project the rest away. For example, the Faddeev-Popov ghosts, the longitudinal modes of the photon, and so on and so forth. And so you can work on a larger space of states, Fock space. For example, a space that contains the Faddeev-Popov ghosts and the longitudinal modes and temporal modes of gauge fields, and the same for gravity, because it's convenient. And to write down Feynman rules and compute diagrams, and then you can say, okay, but at the end I will project these things out, and so I will not consider polarizations for the unphysical modes in and out states. I will not consider polarizations for the Faddeev-Popov ghosts, etc. That is something that you could do paying no price. So you can always restrict your in and out states to whatever you want, but you cannot restrict what's inside there. That's the point. So any restriction you can choose for in and out will collapse there, because most of the times it will not restrict, you cannot restrict the completeness relation. The completeness relation will be this sum here will run over the entire space, physical and unphysical. So you must be lucky or work out a clever projection such that when you project away the unphysical states in and out, they automatically disappear inside. And that is what happens with the Faddeev-Popov ghosts and the longitudinal and temporal modes, and that is what you see in the Coulomb gauge. The Coulomb gauge is useful because in the Coulomb gauge you do not have You don't even need the projection, because we saw that in the Coulomb gauge the propagators have poles only for the physical components, and those plus I epsilons therefore will only see those, which are the two, and there are no propagating degrees of freedom for the ghosts. So for example, take the propagator of the ghosts here. Where was it? This is the propagator of the ghosts in the ordinary gauge, and this has a pole. And if you apply the unitarity equation, you will not see that its delta function will disappear, its contribution. Well, it will compensate with something else, but how to prove it? When you move to the Coulomb gauge, you don't have it, because that is its propagator, and you can put whatever you want there, but the prescription is not needed, it's not necessary. And if you work out the real part, you will have this. This is nothing. So in gravity, we have to deal with a more serious problem of this type, however, because it's necessary to work with the larger Fock space that contains ghosts of a harder type, and the ghosts that you will find are of this type. So you cannot make the two things coexist, but you will have to make plus I epsilon and minus I epsilon coexist. They do not. They coexist only in these identities, but just because you have plus I epsilon on one side and minus I epsilon on the other side, plus I epsilon in this ingredient, minus I epsilon in that ingredient. Otherwise, in Feynman diagrams, these are not Feynman diagrams, these are other diagrams. They are called cut diagrams. But in Feynman diagrams, you cannot have both. But it's necessary in gravity to have things with the wrong sign in front. And then a projection will have to be worked out, and that will be the non-trivial part. So let's see where this well, there is a couple of problems in building a quantum field theory, and in particular quantum gravity. So one will be unitarity, and the other one, which we now describe, is renormalizability. The point is that when you build Feynman diagrams, even in the simple theory that we already considered, the phi to the fourth theory, with the Feynman rules that are written here, everything works fine at the tree level. This is a tree diagram. You can continue using as many vertices as you wish, but there are also loop diagrams, such as this one. And if you take them naively, these loop diagrams lead to results that are infinite. How to compute those? For example, this loop diagram. You can give names to the external momenta, P1, P2, P3, P4, and then you can give a name to the momentum of some internal leg, K, and then the other momentum will be fixed by momentum conservation, where this P will be equal to P3 plus P4, which will also be equal to minus P1 minus P2. And once you have given names to the momenta and imposed the conservation of momentum at every vertex, you just write, apart from a combinatorial factor, the product of the vertices. The two vertices are these, and the propagators inside the diagrams. You do not need, as we said earlier, the propagators for the external legs, because we can stick to the amputated diagrams. So the propagators of this leg and this leg are 1 divided by k squared minus m squared plus I epsilon, and 1 actually I divided by p plus k squared minus m squared plus I epsilon. Now you can see that you have one momentum more than the independent external momenta. The independent external momenta are 3 out of 4, because the fourth is fixed by the other 3, and k is free. Then you have to integrate over all values of k. So there is a k is called a loop momentum, and that is a virtual, the momentum of a virtual leg, because it's not on shell, it's inside diagram, and that can be, doesn't have to satisfy the on-shell condition, so you have to integrate over all of them. Now the point is that this integral is ill-defined, it's divergent. Why? Well, there is no problem at k squared equal m squared when this is 0, or when this is 0, and there is no problem there because I epsilon is a prescription that takes care of that and tells you how to compute, to circumvent those singularities. You can use the residue theorem, and the expression of the integral is well defined for all finite regions of integration. The point is when k squared is large, or p plus k squared are large, or both, or one of them. P is fixed because p is the external momentum, so the only problem is when k is large. What happens when k is large? That this integral is the integral of d4k divided by 2 pi to the fourth. And when k is large, k squared is large, you don't care what m squared is. It's finite, so you don't care if there is a p or not. The dominant term is k squared here, k squared there. And everything else is, so you have 1 divided by k squared, 1 divided by k squared, so you have 1 divided by k squared squared. So for k squared large, let's say much larger than some value, which we will call a cutoff. This is divergent. It's a logarithmic divergent. It's logarithmically divergent. Because you can write this as in polar coordinates like that, so it's equal to the some integral like that. It's ill-defined, and it's the fact that it is divergent and actually how much it diverges can be estimated doing what I just did, neglecting everything, as everything that stays finite. And you can prove that this is correct, even if you can say, but this k squared in Minkowski space could be 0. Yes, k squared could be 0, could be small, could be whatever, but now we are studying, there is no problem when k squared is 0. Here there is a problem, but this is not the correct integral. The correct integral is this one, and here there is no problem when k squared is 0, or when p plus k squared is 0. Or there is no problem when k squared is equal to m squared, so when this is 0 because of the I epsilon. So you can check there is no problem whatsoever in any finite region of integration. But there is a problem when k squared goes to plus or minus infinity. However, the point is that we are not trying to define integrals here. We are trying to define a theory. It's not required to have these integrals well defined. The point is that the theory should be well defined. And if there is a non-observable way to remove these divergences by making a change of variables, for example, that means that those divergences are not there in the theory. They might be there in this integral, but that doesn't mean anything. And this is actually easy to do. And in general, but let's start from this simple example. So let's consider this integral without many factors. They are not interesting for us. So let's forget about the constants. This is 1, this is 1. This is a certain function of p. Now, since this integral doesn't make any sense, we put a cutoff there just to classify the integral. So let's say that we want to define this integral as an improper integral. We would put a bound on the integration domain, and then we will study the limit when this goes to infinity. But we do not study the limit when this goes to infinity in this integral, but in the theory. So we have the freedom to make a change of variable somewhere to remove the problem, if that's possible. We don't know. So we do not want to define an improper integral that doesn't exist. We already know that it doesn't exist. We want to define an improper theory, and that exists. Well, the fact is that if you take a derivative of this object with respect to the external momentum, any component, the result is convergent. Why? Let's do it. So we can exchange the integration with the derivative because this is convergent for lambda fixed. This is convergent, but when I say that this is convergent after the derivative, it will be convergent also when lambda goes to infinity. Let's see it. So if you differentiate with respect to p, there you have the square of the denominator and then you have minus the square, minus 1 over the squared, and then you have the derivative of that, and so you have this. Now, this object admits a finite, well-defined limit when lambda goes to infinity. It's not divergent anymore. First, because there is no divergence at in the finite regions of integration, and the only thing is when k goes to infinity. So k squared goes to infinity. What do you have? The integral d4k divided by what? A k squared here, a k squared squared there, and 1k mu. That's d4k, it's like saying the integral dk divided by k squared. There is one power more in the denominator after you go to polar coordinates, spherical polar coordinates. Let's see, there are 5 k's in the numerator and 6 in the denominator, so you have one more in the denominator. This is convergent when lambda goes to infinity. And that has a very powerful consequence, because in the end you can say that this integral, which is finite for lambda finite, it can be written as the contribution of two parts. A contribution that's finite also when lambda goes to infinity, and a contribution which is not finite, divergent when lambda goes to infinity. So probably instead of f we could call it g, something to avoid too many f's. Let me call it g. This is the definition. So this derivative identity we derived tells you that the derivative of g finite plus the derivative of g divergent is finite, which means that the derivative of g divergent is not divergent, is actually 0. So this divergent part will be some function times the logarithm of lambda, we already know, but anything can be multiplying it, which will diverge with lambda. But that means that the derivative of the divergent part is not divergent, it is finite. So if we isolate the divergent part by saying it is logarithm of lambda times some function of p of lambda, after a derivative that should disappear. So if we parameterize g divergent as log lambda of something, I mean, let's assume that g divergent is purely divergent, because when you separate a finite function into a divergent part and a finite part, you could always, there is no unambiguous separation, so you can always include inside the divergent part a finite part, and it will still be divergent. But you can also, since we have this parameter that you introduced for the improper integral, the cutoff, you can also, by convention, decide that you separate this in a clear way so that this contains no finite part. So the divergent part could be log lambda, lambda, lambda squared, lambda, lambda log lambda. Typically in quantum field theory you will only find logarithms and powers of logarithms, nothing else. Because these are integrals of rational functions, they are simple integrals, and the integral of a rational function can only give logarithms or powers, cannot give anything worse than that. So when you separate the divergent part in a pure way, let's say, you have this conclusion, which means that the divergent part is independent of p. So it's very, very simple. The divergent part of that diagram is independent of the external momentum P. And this was just analyzing, we didn't do any computation actually, it was just very general argument for this kind of diagram. And so when you compute, for example, when is that relevant? For example, it's relevant for this kind of process, which will have a contribution to the lowest order, plus the other contribution that we computed. Then there are many others actually, because there is this one. You can exchange some legs. And then, but the funny story is this, that if you see, this is the vertex minus I lambda, and then you have this object here. Now, this object here is a complicated finite function of P and lambda, plus a divergent part, which we now know very well how to write, because we know that this divergent part. Well, first, how these things, how do they depend on lambda? We dropped the lambda's factors, so there was a lambda squared. So let's recall that in front here there is a lambda squared, and there is a number because there are combinatorial factors. So let me put a number here. We are not interested in these numbers. And what about the divergent part? We know that it is not dependent on P. It doesn't depend on P. It is proportional to log. It has a lambda squared, and it will have another number. Now the question is, can we make an unobservable redefinition so that this sum has a correct, a meaningful limit when lambda goes to infinity, not the integral, this sum. And that is possible because you see that the divergent part has exactly the same form as the lowest order part, which was not dependent on P. So I can reabsorb this in lambda, which is a redefinition of a parameter that is unobservable until I make I connect the theory with the observation. So this is a complicated function of P, and I cannot do anything about that because it depends on P. And if I want to make it disappear, I cannot make it disappear into a constant because lambda has to be a constant. But this is a constant. So the improper sum has a limit. The improper integral has not. And this is for the theory. The theory can be renormalized. All theories can be renormalized because like this. All theories. All diagrams and all theories. Even gravity. But there is a problem for gravity. We'll see. So, first of all, what we said is a very general theorem. these redefinitions of these subtractions, or it's like saying that you subtract, you make a redefinition of lambda basics, basically, which is equivalent to subtract that thing. So you talk about counter terms. And the crucial property that you have to talk about is locality. Locality means that the Lagrangian should be polynomial let's say every term of the Lagrangian should contain a finite number of derivatives. So let me phrase it like that. Every term of the Lagrangian should contain a finite number of derivatives. Of the fields. So you cannot have one of a box function of boxes. Then, if this property holds, you have the locality of counterterms, which is a theorem. The divergent paths of all diagrams are local. Of all the diagrams, with a caveat, but on how to isolate them, but anyway, are local. Since we are in momentum space, derivatives becomes momenta. That means that they are polynomial in momenta, in the external momenta. So they are sums of monomials, each of which depends in a very simple way on derivatives. It's a monomial. So that they are polynomial in the external momenta. For example, in this case, this integral has a divergent path which is polynomial of degree 0. It's a constant. Polynomial has degree 0. But in general, you can repeat the argument and you can check that the divergent part is killed by a sufficient number of derivatives, not necessarily one, but a sufficient number of derivatives. And something that's killed by a sufficient number of derivatives is a polynomial. Why? Because the integrals are always rational functions. So you will have, you can have many loops, then you will have many, say, L loops, many loop momenta, then you will have many propagators. With external momenta, whatever. You can write whatever you want, but it is, since we have assumed that the Lagrangian is made of local terms, every vertex will be a polynomial, every propagator will be 1 divided by p squared. So you will have a polynomial in the numerator, depending on the external momenta and the internal momenta. You will have some denominators like that, and that is your function g of p, and it is clear that a sufficient number of derivatives will kill the divergent part, no matter what. Because anytime you differentiate with respect to the external momenta, you either kill some power of the momentum in the numerator, and that's a polynomial. After a certain number of derivatives, those will disappear. So that is a numerator. It will have some p's. After a number of derivatives, it will disappear. But anytime you act instead on the denominator, you lower the degree of divergence, because you raise the powers of k in the denominator. By differentiating on p, you raise the powers of k in the denominator, because you have p plus k. That's why. And because we have seen it already. So if you differentiate a propagator with respect to p, not k, with respect to p, the external momentum, you get something that falls off more rapidly at infinity. And one after another, one derivative after another, you can obtain an integral that falls off as rapidly as you want. Therefore, after a certain number of derivatives, you get something convergent, which means that its divergent part gets killed by those derivatives, and so its divergent part is a polynomial in the external momentum. There is a caveat here, but we will talk about it in the second